Go. Thank you all for coming, and for those of you still coming through, my name is Michael Lang. I'm a Senior Solutions Architect here at NVIDIA, here in ANZ. I'm joined by my colleague Jeremy Main, who's come all the way from sunny Japan to assist with the presentation, and Blair Breathwaite, who many of you may know, who's very active in the OpenStack community, and he's one of our customers from Monash University. So today we're going to touch a bit on the bit of the why, but also a lot more on the what's and hows of GPUs in OpenStack. And I'm going to kick that off. We're going to have about 10 minutes worth of Q&A at the end, and we have got a couple of NVIDIA AI t-shirts to give away for good questions, so rack them up as you go, put them up at the end. But one of the key whys we often get asked is around, for those of you who don't know, why NVIDIA and why GPUs for computational workloads. And I'm quite surprised it's a question that still arises on a regular basis, but the answer is actually relatively simple. I read the other day that apparently the 80s was meant to be the decade for AI, and the problem was it was massively underestimated, the computational requirements needed to make things work and to make things work well back then. And apparently today, $1 of compute infrastructure today would be equivalent to over $1 million worth of compute infrastructure in the 80s. And we're a key part behind that. So our key claim to fame is our GPUs weren't necessarily designed as a purely graphics engine when we first started the company in 1993. The goal was to have an open architecture that could be leveraged in a variety of ways. And now the massive parallelism we have available on our GPUs is taken advantage of. So for example, our latest cards, which have just hit the market, have over 5,000 CUDA cores available on them, and even some dedicated tensor cores. So we've got the computational requirements there for up to 15 teraflops of single precision, and it's being leveraged in a variety of ways. And in fact, in many ways that we hadn't even initially anticipated. So here's a couple of different workloads that can be applied, and I'll refer to these a few times as we go through this, because it's very relevant in the OpenStack space. So people have known us in the high-performance computing piece for well, basically making things run very, very fast for GPU-optimized code, so it's GPU computing. For virtual graphics and virtual desktops being used as a remote presentation technology for people who either are not on campus, can't get to the same locale as the data, or where the computational workloads are being run, and are using that as a visual interface to visualize complex data sets and the like. Or of course, the big bang one, which is AI, which has boomed over the last few years. And it's probably that AI one which is the more complex, but also the most interesting of them all. So we've seen a variety of use cases that have been driven by our customers in areas that we had never anticipated it. So many people are obviously aware of the AI piece in itself, but not necessarily what it's applied to. We have a name in autonomous driving in cars, but we're not as well known in things like the smart cities or the health and diagnostics, media entertainment, social media, and tools like that. And whether it be education or communications, there is literally an unlimited number of tool sets which AI and our GPUs are being applied to. But what often gets missed in that is the complexities behind the scenes. AI sounds awesome, and it can often sound a little bit too easy, but there are complexities, and there are complexities at the infrastructure stack as well. One of the things that's often missed is the fact that it's not just deep learning as one thing. There are two primary aspects. One of those is the learning itself, which is where you apply an extremely large data set of tagged data to a neural network, and there's a variety of different networks and a variety of different frameworks you can run those on. But once you've done that, there's then the inferencing piece, which is where you apply that learning. So an example of that, I heard recently, Volvo had their self-driving car being tested in Australia, and apparently a large number of automotive manufacturers test in Australia because of our variety of conditions. And the Volvos have something called a LAD, a large animal detection system. And apparently it was driving down the road in sunny Canberra, and as it was driving down the road, it went horse, cow, all good, sheep, not a problem, and then saw a kangaroo and went, peace out, I'm done. I've got no idea what the heck that is, right? And so they actually had to retrain the system. So the cyclic nature of what you do with your data and how you go through this process and your ability to orchestrate those workloads in the data center is actually key, because you don't just do things once, you do things a variety of times. And when you do them, you often need different infrastructure and different stacks being built. So there's a couple of deep learning frameworks up here on the screen, and we'll talk about PyTorch or Torch, Caffe, Theano, TensorFlow. There's ones from Microsoft and Google. A lot of manufacturers have got them. And depending on what you're trying to do, you may need different ones of these. So we've got a fairly significant push to containerization and the like, but your ability on OpenStack to be able to build these up and tear them down and dynamically put them in place as you need them, depending on what the workloads are and what the data is driving, that's a key. And that's one of the reasons we're sort of talking here today. So keep in mind the changes you may have to evidence in your environment. What I'm going to do now is I'm going to pass over to Jeremy, who's going to talk a bit about the what's and the joys of OpenStack and DevStack.
Okay.
And
thank you, Michael.
all right. I'll just have to get you to your presentation. Blair, do we have
Oh,
this?
yeah, sorry. It's all right.
You right?
We're
So it looks like we
professionals.
have quite a large number of people that are interested in adding GPUs into OpenStack environments, and we're really happy to be able to be here with you today to talk about how you can enable GPU pass-through with NVIDIA GPUs with OpenStack. And specifically, I'm going to talk about using DevStack because that's the easiest way for someone to evaluate how to deploy a PLC environment or something just to learn about how to use OpenStack. And DevStack is a very powerful collection of scripts that can build the entire environment on a single server. So as Michael briefly mentioned in my introduction, I'm a solution architect for NVIDIA. I'm based in Japan, and I work with a lot of customers in Japan and throughout the world on interesting and unique problems. And recently, we've been using OpenStack more and more within NVIDIA to be able to give our SAs access to our latest GPUs and in servers almost immediately. So we've liaised with our people in our headquarters to talk about how we're using OpenStack and what was the purpose of us using it and how far back. And the story goes about 3 years ago. We started wanting to be able to use OpenStack to deploy instances using our different GPUs and to allow the SAs to ping someone, and within a few minutes, a VM image would be up with a specific number of GPUs that they could start using. And that flexibility and the ease of building up and tearing down has really been an advantage for the users of this system. So I actually started along this journey with OpenStack maybe a few months ago, evaluating it. Primarily, I'm involved with the graphics virtualization aspect of using our GPUs in virtualization. But more and more, as Michael mentioned, our company is focused on enabling our GPUs to be used for multiple different types of workloads, not just graphics virtualizations, but also deep learning, compute, and AI going through in the future. And I see the cloud as being an enabling technology to allow companies to flexibly deploy large numbers of virtual machines with GPUs to tackle these complex workloads. So, briefly, I'm probably going to go over time, but I'm going to talk about how to build DevStack, and I'm assuming that a majority of you probably already know how to build an OpenStack environment much better than I do. I'm just going to fly through the steps just in case someone needs a refresher. Also, I'm going to talk about some of the configuration changes that need to be made that aren't involved with when you're running the default DevStack scripts. Also, how to check to make sure the GPU pass-through is working. And then I'll show how to actually deploy 2 GPUs and pass through to a virtual machine, and that will be running digits. Okay, so building DevStack, one of the important things that you need to do on your physical host is to make sure your BIOS settings are enabling VTD in the server BIOS, because if you don't, then GPU pass-through won't work because the hardware virtualization calls won't be handled by the system BIOS properly, and you'll have lots of issues. You won't even probably get through the first few steps. I recommend using UBUNTU 16.04. I prefer to use the server version, so that way you don't have any conflicts with the network configuration, network manager, if you install the full workstation image. Next, you need to add some kernel boot parameters to the grub configuration. These are just IOMMU, and also to allow the PCI pass-through to be enabled. And after you do that, you need to update the grub configuration reboot. You don't have to reboot at this phase because there's another change coming up next, which will require a reboot, so you can just save your reboot for a later time. Also, there shouldn't be any NVIDIA drivers installed or running at that time. If you have a fresh Ubuntu server image, it shouldn't have any NVIDIA drivers installed. But just in the case that you do,
it's on the side.
it's on which side?
You gotta just click it towards you.
Okay.
Don't press it all the way.
I'm going to stick in front of here then. A little bit too complex for me, but thank you. So the other thing is you need to blacklist the NOUVEAU drivers. So these will, if you're installing the desktop OS version, you might see NOUVEAU being installed, or not installed, but actually those modules coming live if you have an NVIDIA card installed. While that's nice to have, it's going to impede us in our ability to pass through GPU devices after we run DEVSTACK. So the next part is we need to pull the DEVSTACK scripts from GitHub. That's very easy to do with this git command. For those of you taking pictures, I imagine the slides will be available later, so you can feel free to take pictures if you like. Also, unfortunately, the latest version of the DEVSTACK scripts, I haven't been very successful passing through PCI devices using the latest version, so that's why I have this nice string that I'm sure someone's trying to make a memo of that. We have about 20 more minutes, so good luck. But anyway, that's just making sure we're using a version that we know we've internally tested and it actually works with these procedures. So feel free to emulate this. Next, we need to, after we've pulled down DEVSTACK and we've focused on a specific branch, next you need to modify the local configuration file. This is the default configuration file. You should change the password if you have a internet-facing instance or a server. Also, you need to add these specific configuration items, the floating IP range for the virtual machines, put it whatever you want, or you can accept the default settings, as long as it doesn't interfere with your current IP subnets. And also, in bold here, we have the PCI pass-through filter has to be added to the scheduler options. Then you'll save that. And then you can actually run the DEVSTACK by stacking it. So this will take, it could be 20 minutes, 30 minutes, depending on how fast of a connection you have, or if you're restacking an environment, it'll take less time because you won't have to pull it out all over again. So in the interest of screen space and to make the font still legible, I've really made it very brief about the type of output, but there's quite a lot of output, and if you like watching it, it's great. It looks like you're really busy. It's always good to do that during lunch. Someone's going by, so your screens are going like this. It's like, okay, I'm stacking a bunch of instances. So after the stack, or after the fact, or whatever you want to say, this is sort of a play on words. Those who know me know that I have bad jokes. But after the stack, there's things you actually need to do because in the default DEVSTACK scripts, they're the strings that are used to define the whitelist and also to identify the different PCI devices and give them aliases, that's not parsed well by the DEVSTACK scripts. So you need to actually modify the Nova configuration to add the PCI Express whitelist and also the IDs. So here I've just shown the device ID for the K80. Any of our supported GPU products, you can add the device IDs to that and give it an alias that's easy to recognize. So of course here I'm using the Tesla K80, or just K80 for the alias. Another point to mention is that during my experimentation, I found that some documentation mentioned that you might want to add in the Nova configuration the PCI section and have a different variable name for defining the configuration. I found that that documentation is a little old, and so it's kind of difficult to discern which ones are actually correct. So these are the ones that work for me with this revision. So after you make the change, you need to restart the Nova service. So if you have multiple servers, if you're actually deploying OpenStack instead of DEVSTACK, you would have to have some configuration management tool to modify all your compute hosts and then apply that configuration and restart. This is a one-time thing. You don't need to do this every time. Then you need to have admin privileges to be able to execute all the OpenStack commands. So this is just done at a bash shell. It has to be bash, or well, do yourself a favor, use bash. and just do source, openrc, and then admin, and that'll set a lot of command environment, variables and stuff like that to allow you to access all the commands. Next, we need to initialize the basic networking for the virtual machines. So we're going to create a floating IP address. In this example, we'll only be using 2 virtual machines, one for testing and one for actually rolling out an Ubuntu image. I'm going to reuse that IP address for each of the instances. So you can either memorize the IP address, or anyone that likes to do shell scripting will assign variables to all this output. So here we're just grabbing that IP address that's been assigned to us and assigning it to an IP variable. And next, am I going too fast? Next, you'll create security policies to enable the actual ports, so ICMP and the SSH into the virtual machines. Otherwise, you're not going to be able to get access into your virtual machines when you start them up. So now we need to add a little GPU to the flavor. So I like the name flavor for all these different configurations because it gives it, that nice recipe feel and a nice taste to it. So we're going to add Tesla K80 to this M1 X large flavor. And all we do is just specify this additional property, which is PCI pass-through and then the alias K80 and :1. So the :1 signifies we're going to add 1 device. You can add up to X number of devices in your host. In the Ubuntu example later, I'll show it with 2, so you can add 2 GPUs. So if you just want to make sure that you set that correctly, you can query the flavor to display the output of what the flavor settings are, and under the properties that will list that additional alias. So if you need to update this, you just run that command again, and that'll update that property. So as a sanity check, in building any environment, we have to make sure that we're actually doing the right thing, and we have different checks along the way that make sure we're not going too far along and finding out that the configuration we've created is not going to work at all, and we're just going to end up redoing the OS and starting from scratch again. So we're going to start with the CIRROS OS, and we're just going to assign the extra large flavor and create an instance. And we're going to name that test PCI. Next, we're going to SSH into it after we add the floating IP to that virtual machine. And after we've logged into it, oh, sorry, I didn't add the comment. The password, probably everyone knows for CIRROS is Cubs win with a smiley face. I'm not sure why I have a smiley face there, but I think they did win at one point.
It's more secure.
More secure, yes. Thanks, Blair. So after CIRROS has booted up, it should take about a second. You can run dmessage and then grep the output for NVIDIA's device ID, which would be 10DE. So that's the PCI device ID for NVIDIA. So all of our products are prefixed with a 10DE code. And that will list out that, of course, we've only assigned 1 GPU in this instance, so there's only 1 device that's been detected. So you can disconnect, and then we can delete that. Now we've confirmed that using that flavor that we can actually go ahead and create an Ubuntu instance. So next we need to get the Ubuntu instance, and this is very easy, just wget, and then there's this path where you can download the image, and it's very convenient. After you download it once, you can save it somewhere and copy it to the local file system on each host, or a shared NFS or whatever, however you like to share your files between your servers. And then you need to register this to OpenStack, and so you do this with the OpenStack image create, and then give the disk format and give it a name. Okay. So then when we want to connect to the virtual machine, unless you want to create passwords and stuff like that, it's easier just to give it a SSH KEYPAIR or RSID or RSA ID. So you generate a key, and your key comes out nice and neat. And then to secure that, it's always good practice to make sure anytime you generate a key that you're the only person that has read-write access to that key. So next, we're going to create a new flavor for Ubuntu. Instead of having 1 GPU, we're going to actually add 2 GPUs, and we're going to give it a little bit more RAM and a little bit more CPUs. So we're going to create this flavor, and we're going to call it G1 and then K80X2. So this will be the base flavor that we'll use when we start this instance. So after we create the flavor, now we're going to create the instance, and we specify the new flavor as the argument for creating the server. And then we'll add the floating IP for that server. We're just reusing the same IP that we generated earlier. I've also found that during testing and stuff like that, probably in our bootstrap process, which is coming up in a few more slides, that there's a lot of errors that occur if your host name is not resolvable. So it's just something for me that I think is very helpful, just to quickly add that host name as loopback in your host file, so that way you're not getting these errors. And sometimes when you're trying to sudo, it can't resolve that. And so things kind of take a few minutes or a few seconds for it to complete. So after that, you can do the same lspci command, and your GPUs will be listed. And then you actually need to run this command. This is grabbing a bootstrap command that is created by one of the NVIDIA people in headquarters that has been one of the champions of using OpenStack within NVIDIA. And so this will download Docker and digits and install it and do all kinds of fun stuff. And it will take quite a little bit of time. So please be patient while it downloads and compiles. Then finally, it'll install the NVIDIA driver during that process. And if you use the NVIDIA SMI command, it'll show the actual driver version and the GPUs that it detected. Then finally, you can pull digits using these commands. I'm not going to go through them all. This will also take some time while it's downloading. And then finally, when we SSH'd in to this host, we actually are opening up port forwarding, so that way we can connect to that host at port 8080 in the example here. And that will redirect into the virtual machine to the web interface for digits, so you can actually start to try to use digits, which is one of the applications that you can use for deep learning. We had hoped to do a demo here today, but unfortunately, due to time, I don't think we have the opportunity. If you're interested in learning more about it after the session, you could talk with us, and we can show you more about that. And so that basically, that's how you go about doing that. So at the end, if you have any questions after Blair has finished his part, please feel free to talk to us. Thank you.
We should probably mention too that all of that stuff has been compiled into a lab that you can get to online. And we need to probably update the slides to include the link. So there is an IPython notebook that you can go through to run through all of that yourself. Okay, so I'm from Monash E-Research Centre. I won't say much more about that. Monash is a big university in Australia, obviously, and globally we have a whole lot of research going on too. So as well as having a big student footprint around the world, we have about 7,000 research staff as well. So I work in the E-Research Centre, and we run services and partner with researchers to build the capabilities that they need for their projects. One of the things that we're a part of is the Nectar Research Cloud, and if you were at the keynotes on Monday, then you would have heard a little bit about that towards the end. So Nectar has been running now since 2012 and sort of established this OpenStack community cloud infrastructure for Australian research, and it's a really great story. You can see our usage going up and up in the graph there. One thing that we've done at Monash is leverage Nectar further, not just for the National Research Cloud, but also for some of the projects that we work on locally, and particularly in our high-performance computing. So Nectar's now moving into New Zealand as well. I think I saw Sean come in before. Hey. We use Nova Cells to have a single pane of glass, single horizon, and set of APIs to access availability zones rather than regions, distributed geographically around Australia and now New Zealand as well. So at Monash, we've got 3 of those. First couple were for the Nectar Research Cloud, and the third one, which is where we've built some new interesting capability that I'll tell you about, Monash 3. There's a couple of stories here about some of the science that I guess we've helped support using OpenStack at Monash. I've tried to pick out a few stories that were data or machine learning centric. This is one. This is just a bit of work that we did to help some researchers in the Faculty of IT actually with teaching. So we're running some machine learning tools and notebooks. I think that's a snapshot of an IPython notebook, or rather Jupyter Hub, that they use for undergraduate teaching throughout the semester. So big instances that the students all sort of share. We've also done some cool stuff with digital forensics. So that was a new technique that was pioneered by a couple of researchers in the Faculty of IT to trawl through big piles of data and pick out things of interest, in this case in particular, nasty images. We also had an interesting use case with ANZ Bank, which is of course a local bank here in Australia, looking at what they could do with data mining of FPOS transaction logs. And you can imagine that was a fairly sensitive topic at the time, which is why in the diagram here, you can't really read it, but the three machines on the right-hand side are labeled Monash Research Virtual Server Platform rather than cloud, because they, at the time, the word cloud to them meant it must have been out in the open. That was also, so that work was published, which is nice. And so more recently, as I said, we've built this a new zone of the research cloud at Monash, which is oriented towards high-performance data processing. The main tenant in that zone is M3, which is a HPC service. So M3 is the third cluster in the Massive project, and Massive is a HPC service oriented towards characterization science, which is essentially taking images and doing something useful with them. So that started out, you can see the sort of stats there. We're actually about to upgrade that. And there's a little hint for what's coming. That all runs, of course, using OpenStack to orchestrate the services. The main science use case that system was built for was to support the Ramaciotti Center for Cryo-Electron Microscopy at Monash. They have a Titan Krios electron microscope. That thing freezes samples down to almost absolute zero and then takes a big pile of pictures of them at all different angles and gives you something like that. And apologies for people who have seen these slides before. I know there's a few people in the room that have probably seen these this is probably the third time. But it is pretty cool. They have to pick out, there's a sort of a workflow of image processing that goes on here to pick out the particles and then figure out what angle and orientation they're on, and then do 3D reconstruction so that you can actually figure out the protein structure that's going on there. And that workflow sort of goes something like this, comes off the microscope. We upload into storage and onto the HPC system. The HPC service is actually arranged so that the users of the instrument facility will always have the compute capability ready to go when they need to. So we reserve nodes out and that sort of thing. And of course, they can also take, being orchestrated with OpenStack, we can also give them nodes that they can use as workstations and that sort of thing as well. So that's the image processing side of things. More recently, we've started doing some machine learning on that platform, and in particular with deep neural networks. And I'll tell you a little bit about a story from the Asprey trial, which is a clinical trial that's been going on for over 5 years now. So Asprey's stands for Aspirin in Reducing Events in the Elderly. And credit to Dr. Jason Rigby from also Monash Research. He's the data science coordinator for this project at the moment, or this particular aspect of this project. So Asprey's interesting. They've got over 19,000 participants in this study. All of them are over 70 and healthy when the study started. That's across participants in Australia and New Zealand, Australia and the US. The idea of the study is to determine the potential benefits of low-dose aspirin usage, so particularly for the prevention of heart disease, stroke, cancers, dementia, whether those benefits outweigh the risks of things like gastrointestinal bleeding and stroke that can happen by having too much aspirin. So they take, what have they got, about 300 different variables for this study over the 5 years. Some of these things are free text. So in this case, we're looking at the problem of auto-coding concomitant medications. So it's basically everything else that these people are taking other than aspirin. At the start of the trial, they did not have a good drug database for this to let people select things, so they just took free text, and as you can imagine, they got a whole pile of different stuff. So the workflow is, they've got these entries, they go and stick it in a database, and then they have to get experts to clean it all up and code it back to a standard drug code. And of course, so the big problem is that you have things like Panadol or paracetamol, known as at least 5 different brand names, all sorts of things that people put in, as well as misspelling them and all those other problems. But the interesting thing is that once you have a little bit of data there, you can actually train a neural net on that data and what the correct answer was, and get it to do the correction for you. And so what Jason did is he built a model and trained it with TensorFlow, and then you can actually see the result that he's put together for that part of the study. So he did that, and he did that work using M3. So it just so happens that this machine that we built for the characterization science is also actually quite good for DL as well. I'm going to skip over this stuff because Jeremy already covered it. One of the key things is once you've sort of configured all your pass-through stuff, don't forget the tuning as well. I should mention that the guys from OVH did a talk yesterday morning where they went into some more detail on this. This is just a snapshot that highlights, this is not GPU or CUDA high-performance LinPack. This is just regular CPU-based LinPack. But the green line, so the blue line at the top is the performance that you get once you've done the CPU pinning, the CPU model, the NUMA topology. That's the LinPack performance you get relative to bare metal for this configuration. So that's relative to 1 being right at the top there. And once your matrix size goes up, you start getting to 99%. But the green line shows what happens when you get the NUMA configuration wrong, and so that's when you swap the NUMA nodes. So you've got one CPU operating off the memory of the other, essentially. So that illustrates that cost. And that's going to be pretty important for you if you're moving data between main memory and GPU as well. So I've also got a little performance snapshot here, courtesy of Malnox, that shows TensorFlow performance bare metal versus virtualized, so versus PCI pass-through. They did this with OpenStack Pike in the lab, using two machines over the network, doing distributed training with K40s. And you can see that there's virtually no difference in performance for that particular workload. So we've been doing this GPU pass-through stuff now in production for maybe 3-4 years now, but for M3, we've been doing it for a year and a half or so. There are a few rough edges with PCI pass-through that you need to be aware of. In particular, when you do PCI pass-through, you're giving the whole device to the guest, so you no longer have any hardware monitoring on the host side. There's also a bunch of issues to be wary of and that are not really documented anywhere in public with regard to security and PCI pass-through. The main thing being that the device drivers sort of assume that root privileged code in the OS should be able to access basically the whole config space of the device. That means that you can do all sorts of things to basically, I guess, brick the device that would then require a PCI reset to get it back. And there's a whole bunch of registers there that really should be fenced off by the MMIO, but none of that is implemented into public KVM. So I think it's interesting to see now a few public vendors starting to come out with possibilities for pass-through on their clouds. They should probably be wary of this and looking to try and maybe implement that upstream functionality as well. And I'd certainly be interested to talk to people that are interested in looking into that. One of the other major problems too is that you cannot do PCI GPU direct peer-to-peer if you've got multiple GPUs pass through to a single KVM instance. For one thing, in the default guest PCI topology, you can't even see that this is possible, so the device driver is unable to, it doesn't know this. But if you happen to want to do this and you have a spare couple of $100,000, then you can buy yourself a DGX1 or indeed some sort of IBM box that has NVLink in it, and then that will work. So that DEVSTACK rigmarole that Jeremy just took us through before, we have actually done that on the DGX, and so this is a little snapshot sort of showing what happens once you've got your Ubuntu instance running here. Then you'll see so the connectivity matrix from the NVIDIA SMI command inside that guest shows that we have NVLink connectivity between all the GPUs, and we can do peer-to-peer. There's a little snapshot showing you some of the latency numbers. So I'm going to leave it there, and hopefully we'll have 1 or 2 minutes for a couple of questions if anybody's got them.
Share the link
For the lab? Oh, God. Yeah, I guess we'll, actually, you know what I can do? So I skipped over this before, but so the wiki OpenStack GPUs, I put that page up just the other day, which pulls together some information that's come from various forum sessions and so on at the last couple of summits, particularly around configurations for PCI pass-through that are known to work. So that's host OS GPU models and ones that don't. And I'll put the link on that page. Yep. Anyone else? Yep.
It's a question mainly for NVIDIA. So in relation to NVIDIA Grid and the ability to virtualize GPUs for running CUDA, where are you guys at with that on the roadmap? So I know it can be done for VDI. So what about virtualizing GPUs for CUDA execution?
So yeah, there's a couple of answers to that.
The short answer is yes, that's coming.
Yeah, correct.
Yeah.
So we've got it working right now. It depends on the hypervisor. Hypervisor support is critical. In terms of where we're at with OpenStack, we're close. We're getting some work done on KVM through Red Hat, and that's in the pipeline. Can't give you an exact ETA. There's all sorts of release controls that are actually not fully in our space, but we are working very hard on that. We're actually seeing an increased push from universities and the like around the world, so it's clearly on our agenda. Look, it'll probably be both Maxwell and Pascal, but at release that'll come out. Pascal's our current supported platform on Grid, so you can assume that's the case, and I'm making the guess it's going to be backwards compatible on Maxwell at least. So yeah, that should be pretty soon, hopefully. Cool. There's another one on that side? Right, cool. You get a t-shirt for that. Good question. Questions?
I wonder if that is something you're looking into
Sorry, I missed the first bit.
So the question is that basically what about Cyborg? So Cyborg is a new is a proposed accelerator management service for OpenStack, and yes, it looks like a good idea. I didn't realize that any session. I hadn't seen the session. Right. Okay. As far as I know, there's nothing sort of working or anything there yet. Today, you just have to use the PCI framework that's already in Nova. I know that the Nova guys they don't like the PCI framework that's there now, and hopefully the Cyborg folks are watching what Nova's doing with placement and that sort of thing, and trying to make sure that they're designing for that. But I don't think there's anything ready to run yet.
So in the Horizon framework, when you're looking at the dashboard, I'm not sure if this is on or not, one of the things that's missing is that GPU is still not considered a primary resource to be considered in the dashboard. So you can see how much CPU resources you have, how much memory, how much storage overall per host. But we don't have the ability to find out how many GPUs are available to be assigned or how many GPUs are actually assigned to virtual machines. So that's something that is definitely impeding us internally using OpenStack, because yes, we have demand, but it's hard for us to gauge through the dashboard to find out how many resources are available of different types of GPUs. It's easy to do per host if you log into each host and query it. So maybe Cyborg, I'm not sure if that's something that hopefully the GPU can be part of the solution or more interwoven into these different metrics that are being reported by each of the hosts. So hopefully we can influence that.
Yeah, well, I could imagine Cyborg having a way to control the host side vGPU elements once that's ready to go. So, for example, maybe being able to tell through Cyborg reconfigure a GPU into a different vGPU profile based on what you're asking for with your instance.
Yeah, from what I could tell in hype, at the end of hype, that's when vendor like NVIDIA could do some API.
No, it's definitely possible. But the thing is, well, as far as supporting vGPU on OpenStack, we've publicly shown that we've submitted patches for upstreaming. And it's just a matter of us having to wait for when those will be integrated into a release of KVM in a kernel by Red Hat. So that's why we're waiting. It's not a technical limitation on our behalf. It's just a matter of our partners having to implement these things and go through the motions, as they say. So how many people have interest in doing VDI with OpenStack as opposed to virtualizing servers or doing other tasks? Okay, it's about quite a number. So in the case that you're using in VDI, what would the remoting protocol you would use to connect to those? Because that's often the question. If you're using a commercial hypervisor or one of these other solutions, you have to have a way to connect to those desktops and serve either virtual desktops or applications. So if anyone has an opinion about what remoting protocol you're planning on using, or if it's still something you're considering, I'd like to hear. And maybe this is not the right Q&A part to discuss that, but if you have a loud voice and want to volunteer some information, I'd be interested in hearing.
Guacamole looks pretty good.
Well, it tastes good with chips or GPUs. Well, there was nice DCV, so that was something that was fairly independent as far as a protocol. Just VNC with a nice layer that used our encoding and capture APIs to accelerate the delivery of the desktop, that remoting protocol. That was bought out by Amazon, a year and a half ago or something like that. So there are alternatives to the commercial hypervisor and their remoting protocols and their solutions. But if guacamole, I don't have any knowledge of that. I'm going to check that out maybe later on tonight. Not the one that you eat with chips, but I hope you're not pulling my leg. But anyone else have a remoting protocol that they use besides VNC or If you're using Linux, I guess you can use X or something like that.
You guys using VNC?
Yep.
Okay.
And with virtual GL. Can I unplug?
Instead of approaching the GPU pass-through with a flavor that will have the GPU, do you see a better way of doing that where you decouple your choice of CPU and memory from the request of the GPU? So you say maybe, yes, I want this amount of CPU and RAM with the extended capability of the GPU. Is there a better way to do that scheduling?
Is there a better,
Yeah, I mean, I think that's one of the objectives of Cyborg. So to start treating those accelerator resources as first-class citizens, independent of Nova instances, and I mean, some of these devices can be hot plugged as well. So there's actually no need to tie the lifetime to a guest.
If there's no other questions, thank you very much for your time today, and thank you.